Hello, welcome back to Fundamentals in Ecology. My name is Umesh Srinivasan and I am at the Center for Ecological Sciences at the Indian Institute of Science. And today, what we will be talking about is something that is central to ecology. It's a concept that is central to ecology and especially community ecology, which is the concept of the niche and the fundamental and the realized niche of an organism. Now, this is a term, niche, that I'm sure most of you would have heard multiple times before. And that's with good reason, because the concept of the niche is really important when we are talking about exploring patterns and processes in ecology. But it's important to realize that the word niche is used differently by different people, and what it means to one person might not mean exactly what it means to somebody else, because there are multiple definitions of the niche. In 1917, Grinnell came up with the definition of a niche, which he said was a distributional unit within which each species is held by its structural and functional limitations, and that comes, this description comes from his observation of a bird species called the California thrasher, which is restricted to chaparral habitat on the west coast of the United States. Now, so what Grinnell is saying is that the California thrasher is adapted to chaparral habitat, and therefore, because it's adapted to chaparral habitat, it cannot expand its range, it cannot leave chaparral habitat and expand its geographical range to other habitats. And so therefore, this is very much a habitat niche concept, where Grinnell is saying that the California thrasher is restricted to chaparral habitat. So the chaparral habitat is the distributional unit within which the California thrasher is held because of its structural functional limitations that prevent it from utilizing other habitats. This is a very common way in which we describe species. We might say this is a rainforest plant or this is a desert bird. What we're actually saying is we're describing the habitat of this species. So there is a habitat niche concept proposed by Grinnell in 1917. 10 years later, Elton described the niche as the status of an animal in its community, which is a functional niche concept. So what Elton is saying or asking is this animal a predator? That is the role that it plays in this community. So that's the status of that animal in the community. The status is that it is a predator or a primary consumer or a herbivore or a producer and so on. So that is the functional niche concept that Elton proposed 10 years after Grinnell's habitat niche concept. Perhaps the most widely used concept of the niche is that of Hutchinson's. In 1958, Hutchinson said that there are a number of environmental variables. You remember our definition of what is called a condition, which is an abiotic environmental variable that cannot be consumed. But Hutchinson says that every species is adapted to survive and reproduce in a certain temperature range, in a certain rainfall range, in a certain, let's say if it's a plant, a certain range of soil nitrogen, a certain concentration of carbon dioxide and so on. So there are n axes representing n environmental variables, and a species can survive on certain parts of those n axes. So if you have, let's say, temperature, for example, and a species adapted to 20 degrees Celsius to 25 degrees Celsius, then and it can only survive and reproduce in that part, then it will exist on the temperature axis only between 20 and 25 degrees Celsius. If that same species is adapted to rainfall, between 2000 and 3000 millimeters of rain annually, then you're adding another axis on which this species can or cannot exist. So now you have two axes. You have an axis of temperature, you have an axis of rainfall. And therefore, this species now with both these axes combined can survive between 20 and 25 degrees Celsius and between 1000 and 2000 millimeters of rainfall. So even if there is a locality on Earth where the temperature is 23 degrees Celsius, but the rainfall is 500 millimeters, then that species is not going to be able to survive in that location, even though the temperature space is okay for that species, the rainfall space is not. Therefore, if you add more and more axes like this, what you end up with is what Hutchinson called an n-dimensional hypervolume, which is a temperature axis, a rainfall axis, a carbon dioxide axis, and so on. And so what you have is a niche that is determined by multiple environmental abiotic factors. Here's an example of that. The n-dimensional hypervolume is all the environmental conditions under which a species can maintain a population growth rate greater than or equal to 1. If population growth rate is greater than 1, population is growing. If population growth rates are equal to 1, the population is at the same size. If population growth rates are less than 1, then the population will decline to extinction. So Hutchinson's definition of the niche is saying, what are all those environmental conditions under which a species can maintain a population growth rate greater than or equal to 1, can persist indefinitely, can remain in that location without going extinct. And the n-dimensional hypervolume says there are no limiting factors on the resources that the organism of that species can use, which is that if I need temperatures as an organism between 20 and 25 degrees Celsius, then there is no other factor, there is no external factor that is preventing me from occupying some temperature spectrum in that. There is no species, for example, that displaces me between 20 and 22 degrees Celsius such that I am only present between 23 and 25 degrees Celsius. So there is no limiting factors on the resources that the organism can use. Here is an example of two species of algae, and what you have on the left side is you've got two axes, axis 1 and axis 2. If you look at axis 1, it intersects with axis 2 at 0, at a point 0, 0. And if you move towards the left along axis 1, you are increasing dissolved nitrogen, increasing phosphate and turbidity. So you've got those arrows, the red arrows pointing towards the left, which means that as you move along axis, pointing towards the right, which means that as you move along axis 1, those arrows that point towards the right are positively correlated with axis 1. And those variables in this case are things like dissolved nitrogen, phosphate availability, turbidity of the water that we are dealing with. As you move towards the right on axis 1, other things are actually decreasing. Those are arrows that are pointing towards the left. So water temperature, salinity, for example, are declining, are decreasing as you move towards the right on axis 1. And so what you've got is multiple environmental variables that you're measuring, collapsing the variation in those multiple environmental variables onto two axes and asking where do, for example, two species of algae fall in this n-dimensional hypervolume. And what you've got to the left is a species of algae called Leptocylindricus. What you've got on the right is a species of algae called Skeletonema. Leptocylindricus tends to be on the negative side of axis 1, which means that if you look at the graph on the extreme left, it seems to prefer negative values of those environmental variables on axis 1. So it seems to prefer lower temperatures, lower salinity, whereas skeletonema seems to be at the area where it is found, where skeletonema is found, is close to 0, 0. So skeletonema occurs, its niche, its fundamental niche is areas where dissolved nitrogen, phosphate, turbidity, salinity, etc. are average, are somewhere in the center. Whereas Leptocylindricus prefers habitats that are a little more extreme in terms of all of these various environmental variables compared with skeletonema. So this is one way of thinking of the fundamental niche, which is all the environmental conditions under which a species can maintain a population growth rate greater than or equal to 1. Now, the fundamental niche of a species should be related and is related to where it is found geographically. So, if a species is adapted to warm, wet temperatures, if that is the fundamental niche of the species where it can maintain a population growth rate greater than or equal to 1, then that species should be found in habitats like rainforests. It should not be able to colonize habitats like desert. It should not be able to expand its range to adapt suddenly now to hot, dry conditions. And so, the fundamental niche of a species is related to where the species is found on Earth. But it's not essential that if the fundamental niche of that species is related to things like temperature and rainfall and so on, let's just take temperature and rainfall as two examples of that n-dimensional hypervolume of those n axes. It doesn't mean that if you would expect, based on the physiology of the species, based on its temperature and rainfall tolerances, you might expect that this species would be found over a geographical range of 250 square kilometers. It's not necessary that that species is actually found across 250 square kilometers. Its actual range could be 150 square kilometers. So that then becomes the realized niche of the species. So there is a fundamental niche, there is a species' ability to tolerate multiple environmental conditions, multiple parts of environmental conditions. That's the fundamental niche. But it might not occur everywhere where those conditions are suitable for the species, because maybe there is another species that is competing with it and preventing it from colonizing or occupying part of its range. That then becomes the realized niche, which is the environmental conditions under which a species actually exists in the presence of biotic interactions like competition and predation. These organisms that you're seeing on the slide here are barnacles. These are organisms that live in intertidal rock pools. So if you go to a coast, and in this case a coast in Europe, if you go to a coast with the water coming in during high tide and the water leaving during low tide, what you have on the coast are small rock pools. These pools fill up during high tide and then the water recedes during low tide, and these pools are occupied by these barnacle species. This is a classical experiment that Joseph Connell did, published in 1961, on two species of barnacles, Thamellus and Balanus. Now, Connell went to these intertidal pools and observed that Thamellus is found in the upper part of the pool and Balanus is found in the lower part of the pool. So just imagine the wall of a swimming pool, for example, and you've got at higher parts of that wall you've got Thamellus, and at the lower parts of the wall you have Balanus. What Connell did was that he removed Thamellus and asked he removed Balanus and Thamellus, and he asked what happens to the distribution of the other barnacle species if you remove one of them. So when actually you remove Balanus from the lower part of the pool, Thymallus is able to expand its range, able to colonize the lower part of the intertidal pool as well. So the fundamental niche of Thymallus encompasses the entire depth range of that pool, but it's not able to occupy its fundamental niche fully because Balanus is preventing Thymallus from expanding into the deeper parts of the intertidal pool. This is something called competitive exclusion, and we will get into what that is when we talk about competition. But basically what you have is a difference between the fundamental niche and the realized niche of this species. The fundamental niche of Thymallus is far larger than its realized niche because of a competitor, because of a species coming in and preventing it from utilizing its entire fundamental niche. On the other hand, the fundamental niche of Balanus and the realized niche of Balanus are the same. So if you remove Thymallus from the higher parts of the intertidal pool, Balanus does not colonize the higher part of the pool. So actually the fundamental and the realized niches of Balanus are the same. Competition has been at the heart of community ecology theory for a long time, and it was always assumed that a species would have a fundamental niche based on its physiological properties, for example, and that the realized niche of the species would always be smaller than the fundamental niche. And that is because what you have is competition, predation, that makes the realized niche smaller, prevents the species from occupying all the parts of the fundamental niche that it can occupy. So if you look at that a little figure schematic on the top over there, what you've got is the fundamental niche described in the dashed circle. So a species can occupy all of that space. You can also think about that in terms of geographical range sizes, that the species can occupy that entire range. But what you have is competition, predation, disease and so on, preventing that species from occupying the entire range that it can, or occupying its entire fundamental niche. And therefore the realized niche, which is the grey circle, is smaller than the fundamental niche. And classically, ecologists have thought of the realized niche as being always smaller than the fundamental niche because there are all these other biotic processes like competition, for example, that reduces the size of a species niche. But you can also think of the realized niche as being larger than the fundamental niche, which is a little bit counterintuitive, because if you're saying here is a species that can survive and reproduce and persist indefinitely in these conditions, how can the species expand its range or expand its niche to survive in conditions where physiologically it is not adapted to? This comes about by facilitation. We will talk about competition and facilitation, but facilitation is the process by which one organism is helping the other. One organism is making conditions more favorable for the other organism. A great example of this is coral. Coral is actually two organisms, a zooxanthellae and a polyp, and both these organisms come together in a mutualistic relationship. And when they do come together in a mutualistic relationship, they're able to occupy places, they're able to occur in places where each of them alone would not have been able to occur, would not have been able to colonize. Right? So this is an example of a symbiosis or a mutualism that actually allows both of these organisms to be present in a location where either of them on their own would not have been able to occupy. And so what you have is each of those species having a fundamental niche on its own, independently having a fundamental niche, but through things like resource enhancement, making the water, let's say, less turbulent because of these physical structures, this species is actually able to be present in locations where it wasn't. So the realized niche can actually be larger than the fundamental niche. So that is the fundamental and the realized niches, and based on the size of these niches you can classify species as being either generalist or specialist. And when we talk about generalists and specialists, we're talking about niche breadth. We're talking about the range of abiotic and biotic conditions under which a species can occur. Generalists have wide niche breadths, specialists have narrow niche breadths. So generalists can occur under a wide variety of conditions, specialists cannot occur under a wide variety of conditions that are restricted to a small set of environmental conditions. So an example of that is here on the right with two species of babblers. You've got the dark-fronted babbler, which is on the top right there, which is a habitat specialist. If you look at in terms of temperature and rainfall, where it is found in that temperature rainfall space, it's found in humid warm conditions. The humid warm conditions are found in the Western Ghats and in Sri Lanka, and so the range of this species is the Western Ghats and Sri Lanka. It's adapted to warm humid regions, and so that's its niche, that's its temperature rainfall niche, it's a specialist in that case. Whereas if you look at the other babbler here, the tawny-bellied babbler, the tawny-bellied babbler is adapted to a wide variety of temperatures and rainfall regimes, and because it is adapted to both low temperatures and high temperatures and low rainfall and high rainfall, it is a generalist. It is a temperature and rainfall generalist, and that physiological adaptation to these environmental conditions actually maps on to the geographical range of the species, right? The habitat specialist is far more likely to have a restricted range than a habitat generalist, which should have a large geographical range because it is adapted to a wide variety of environmental conditions. In terms of talking about niches, niche overlap refers to the extent to which two species share resources relative to their overall resource use. So you can see that the dark-fronted babbler and the tawny-bellied babbler have a little bit of overlap in temperature and rainfall space that they're using. The two circles have some overlap. There is a certain amount of temperature and rainfall space where the tawny-bellied babbler and the dark-fronted babbler are both present, or they're both using that space. The greater the niche overlap between species, the greater the likelihood of competition between those species, because they are likely to be competing for the same resources. Of course, that's assuming that all those two species are of the same trophic level, they require the same resources and so on, but we'll get into that in more detail when we talk about competition. But just the fact that two species share space, the more space they share, the more likely competition is present in that location. So we will get into competition later on, but the next time we meet we will talk about community assembly. So thank you very much for being here, and see you next time.